The Arrhenius equation is basically a mathematical relationship that relates the rate constant K to the activation energy, which is EA. The Arrhenius equation is given as K equals A times e to the power of negative EA over RT. A is the frequency factor, or likelihood that collisions occur with a proper orientation. EA is the activation energy. T is the temperature in Kelvin. R is the gas constant, which is 8.314 joules per mole per Kelvin, or 8.314 times 10 to the negative 3 kilojoules per mole per Kelvin. If we were to take this equation and we take the natural logarithm of both sides, the equation would become ln of K is equal to, and you should try this on your own, we'd have ln of A times e to the negative EA over RT. If we simplify this using our log rules, we'd have ln of A plus ln of e to the negative EA over RT. And then that simplifies to ln K is equal to negative EA over RT plus the ln of A. This represents a straight line equation. So y would be ln K. Our slope m would be negative EA over R. Our x is 1 over t. And our y-intercept b is ln of A. If we were to graph this relationship, our y versus our x value, we'd have ln K on the y-axis, 1 over t on the x-axis. This would give us a straight line with a downward slope. The slope of this line then is negative EA over R. When K is determined experimentally at several temperatures, the activation energy can be calculated from the slope of this graph. We can also use the Arrhenius equation if we have two temperatures and two rate constants. What we're going to do is take the Arrhenius equation, and if we write it out twice and then take the difference between them, you don't really need to worry about how we get this new equation, but it's going to be the ln of K2 over K1. So where K2 is the rate constant at the second temperature, K1 is the rate constant at the first temperature. That's going to be equal to negative EA over R times 1 over the second temperature minus 1 over the first temperature. This is a way to figure out the activation energy without graphing the relationship. Here's one example problem then. We've got a rate constant for the decomposition of hydrogen iodide determined at two different temperatures. At 650 Kelvin, the rate constant is given as this, and at 700 Kelvin, we have a second rate constant that was found. It says to find the activation energy for this reaction. What we're going to do is use that equation then. Ln of K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. Our two rate constants then we're plugging in. So K2 and K1. We don't know EA, we're solving for that. We're going to put in our R, our gas constant value. And then we've got T2 and T1. So if we were to solve that, we get 180,000 joules per mole, or 180 kilojoules per mole. And that would be our activation energy.